Section 10.1, infinite series. Given an infinite sequence, then the infinite sum is, this is summation notation, this is sigma notation, and it's n equals 1 to infinity of a sub n. And that's equal to the first term plus the second term plus the third term plus the fourth term, keep on going. And we're going to do this infinitely, and we're going to see if it converges to a sum or does it shoot off to infinity. And it says which is an infinite series or just a series. Well, as we go through these notes, let's look at a specific example. And I have a specific example on the next slide. It's the sum of 1 over 2 to the n from n equals 1 to infinity. So let's write that. N equals 1 to infinity of 1 over 2 to the n. So this is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32. Now I'll tell you right away that this series actually converges, and I know that because what we're adding on is getting smaller and smaller and smaller. It's heading towards 0. So the limit of the terms themselves is 0. So once you get way out to 1 over 512, that is getting really close to being 0. Now if you add on something that's getting bigger and bigger and bigger, instead of getting smaller, that one will shoot off to infinity. A series is a sequence of partial sums. A series creates a new sequence. The partial sums of a series form a sequence. So we're going to look at these partial sums. So the first partial sum for our specific example is just 1/2. It's the first term. The second partial sum is 1/2 plus 1/4. Now that's 2/4 plus 1/4 is 3/4. The third partial sum, we take the 3/4 and we add on 1/8, which is 7/8 when you do common denominator. The fourth partial sum is 7/8 plus 1/16, which ends up being 15/16. And then the fifth partial sum is 15/16 plus 1 over 32, which is 31 over 32 when you do common denominator. Now that partial sum has some sort of value of real numbers, each defined as a finite sum. So there's a new sequence going on here. We have 1/2, 3/4, 7/8, 15/16, 31 over 32. Now those are all finite sums, but that's what creates the new sequence. Now the series is going to converge to whatever these are converging to, and these are actually converging to a value of 1. 31 over 32 is already very close to being 1. If the sequence of partial sums has a limit s as n approaches infinity, which it does in this case, it's going to 1, we say the series converges to the sum s, and we could write this. We could say that the series has a limit. It has a sum. Otherwise, we say the series diverges. If the sequence of partial sums converges, then the series must converge also. The sum of series, which is, when it exists, is not the limit of the terms themselves originally, but the limit of the partial sums. Now, if we go back to the original terms, the limit of those original terms was going to 0. That's part of the reason why this actually converges, because we keep adding on less and less and less and less. Given this series, find if the series converges or diverges. Well, we know that it does converge, but what is the sum? Well, let's take the limit as n approaches infinity. Can we find a formula for the sequence of partial sums? Wrong button. There we go. Back to the beginning. Well, look how the bottoms are the powers of 2, and the tops are 1 less than the power of 2. So we can write a little formula to represent the sequence of the partial sums. The bottom was the power of 2's, and the top, that's the power of 2's minus 1. In order to find the limit, let's multiply the top and bottom by 1 over 2n. We have the limit, as n approaches infinity of 2 to the n over 2 to the n minus 1 over 2 to the n over 2 to the n over 2 to the n. Now that's the limit as n approaches infinity of 1 minus, well, we'll just leave 1 over 2 to the n over 1. That's equal to the limit as n approaches infinity of, well, let's plug in infinity. We don't need this again. Let's plug infinity in for this n over here, and we get 0. 1 minus 0 over 1. So there again, the limit of the series is 1. So that's what the sum is. Let's take this series again. This is actually a geometric series. And what if we wanted the nth term? That's a times r to the n minus 1. So the first term is a half. The second term is a half, or the ratio is a half. The second term is a fourth. Raised to the n minus 1 for n greater than or equal to 1. Geometric series, if you start at 1, you have ar to the n minus 1. If you start at 0, you have a times r to the n. Well, let's take the partial sums. Partial sums, the first term plus the second term plus the third term plus the fourth term. And since it's geometric, the way you get the next terms is you keep multiplying the first term by r. Then r squared, and then r to the third, and so on. What if we multiplied both sides by r? We would get, this would become ar, this would become ar squared, that'd be ar to the third, and so on, just like we have right there. Then the next step in what we're trying to show here is we subtract these two. When you subtract these two, you get a minus, well, there's no a to subtract from, so you get a. And then ar minus ar goes away. Ar squared goes away. All these go away, and right here there's going to be a to the n, or a r to the n right before this one that will cancel out, and you'll get minus this one right here. That's that. On the left side, we can factor out an s sub n and then divide by 1 minus r. Let's look at a minus ar to the n plus 1. Now, just the r to the n plus 1 will go to 0 if r is between negative 1 and 1. So let's look at what if r was 1/2 to the n plus 1, and n is shooting off to infinity. So this piece goes to infinity plus 1, which is infinity. Imagine if this piece was 1 over infinity. That's actually 0. So this would just become a minus a times 0, which is a. But this has to be a fraction less than 1. And what you end up with is the sum of a geometric series is a over 1 minus r, as long as r is in between negative 1 and 1. Now, saying r in between negative 1 and 1 is the same as saying the absolute value of r is less than 1. Does that series converge? Well, it's a geometric series, so we can approach it a new way. We can say that a sub 1 is equal to 1/2, and the r, what we're multiplying by, is 1/2, and that's less than 1. So the sum is equal to 1/2 over 1 minus 1/2. Now that's 1/2 over, well, 1 minus 1/2 is a half. So there's another way to show that this series is converging to a value of 1. Geometric series test. A geometric series is in the form, this form or this form, and then a cannot equal 0. The geometric series diverges if the absolute value of r is greater than or equal to 1, and if the absolute value of r is less than 1, the series converges to the sum, this right here, that little formula, a sub 1 over 1 minus r. Example, determine whether the following series converges or diverges. This is a geometric series. A sub 1 is, well, when we plug 1 in here, we get 3/2. And then the next one, so 3/2 is a sub 1. Then if we plug 2 in, we get 3 over 4, then 3 over 8, then 3 over 16, and keep going. We're actually multiplying by 1/2, which is less than 1. The sum is equal to a sub 1 over 1 minus r, which is 3/2 over 1/2, which is a value of 3. Letter B is also a geometric series. A sub 1 is 3/2 when you plug 1 in. But then it goes 3/2 plus 9/4 plus 27/8 plus 81/16 plus keep on going. So what you're multiplying by is also 3/2. But that's greater than 1. What you're adding on gets bigger and bigger and bigger. It doesn't get smaller and smaller. So this series, the sum is shooting off to infinity. But we just say that this diverges. Now, if you forget about this fact right here, and you continue on and just say, well, I'm just going to find the sum anyway, you can get a value for that. That's 3/2 over 1 minus 3/2, which is 3/2 over -1/2, which is -3, but that's completely wrong. The sum is not -3. The sum is infinity, shooting off to infinity. So be careful that you don't continue on and give me a value for the sum when there really isn't one. Nth term test for divergence. If the limit as n approaches infinity of a sub n does not equal 0, then the series diverges. Note, this does not say that if the limit equals 0, then the series converges. It doesn't say that. This test can only be used to prove divergence, not convergence. If the limit as n approaches infinity of a sub n equals 0, then this test doesn't tell us anything, and we need to use another test. Example, determine whether the following series converges or diverges. We take the limit of the nth term. This is the nth term test, which is 2n plus 3 over 3n minus 5. Now the limit as n approaches infinity of this one is 2/3, which does not equal 0, so this diverges. The limit as n approaches infinity for this one is n factorial. We have n factorial over 2n factorial plus 1, and we're going to divide everyone by n factorial. So we have n factorial over n factorial over 2n factorial over n factorial plus 1 over n factorial. We have the limit as n approaches infinity of 1 over 2 plus 1 over n factorial. Well, the n factorial is going to shoot off to infinity, which makes that little fraction go to 0, so the value is 1/2. That does not equal 0, so we say the series diverges. And on the last one, it's very similar to the one we just did. We have 3 to the n minus 2 over 3 to the n. We have the limit as n approaches infinity of 3 to the n over 3 to the n minus 2 over 3 to the n over 3 over n, 3 to the n over 3 to the n. We have the limit as n approaches infinity of 1 minus 2 over 3 to the n over 1. Now this becomes 0 as n approaches infinity, so that's 1. That doesn't equal 0. This one diverges. Oh, and we should say, and I want you to say, diverges by nth term test. So I want that on all of these. So diverges by nth term test, and I want this because we're going to have a bunch of tests in this chapter. Diverges by nth term test. Now there's 3 that diverge. Well, those are 3 where the limit is not 0. But what about one that is 0? What about n equals 1 to infinity of just 1 over n, which is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus keep on going. Now, look, the nth term is converging to 0. And we can write that. We can say limit as n approaches infinity of 1 over n is equal to 0. Now, if the nth term test is equal to 0, we don't know anything. That doesn't tell us anything. This test is for divergence only. We can only determine divergence by the nth term test, unfortunately. This one, we'll talk about this later, but this is the harmonic series, and this one actually diverges. Even though you're adding on less and less and less, the less doesn't get less fast enough. The terms are not approaching 0 fast enough, so this one actually does not converge.